So with all of the symmetry that exists in the magnetic electromagnetic world, it's not surprising that we're going to run into another symmetrical operation here, which is that what we just talked about with electric motors, we can flip that all upside down and talk about electrical generators. So we talked about a motor in some detail, so I'm not going to go through the motor in quite as much, or the generator in quite as much detail, but I want you to see how similar they are in their operation, because it gives you a real nice sense of that, the symmetry of magnetic and electrical forces. So a motor uses a current within a magnet field to create work, to create movement. A generator uses movement within a magnetic field to create a current. So it's working exactly opposite. This is like an electric car, that you have a battery that creates a current and that leads to the movement of the wheels. This is like one of those great windmills in which you use the movement of the windmill to turn a rotor that moves within a magnetic field, and that creates a current that generates electricity. So we have Faraday-Lenz's law. This is really crucial to how a generator works, because it's going to tell us what the voltage is. As the wire loop gets turned, right, here we're turning this here, what's happening to the flux through our loop? It's changing, right? When it's oriented parallel to the field, there's no flux. And then when it's perpendicular, there's a bunch of flux, and then there's no flux, and then there's a bunch of flux in the opposite direction as you get around 180 degrees. And so as long as this is constantly turning, the flux through your loop is constantly changing as well. That's what creates a voltage. Okay, so that's how a generator works. So a motor we can think of is a effect of Lorenz's law, right? The law that tells us what the force is going to be when we have a moving charge, a charge moving through a magnetic field. A generator depends on Faraday's law, and so you can see how those two are sort of mirror images of each other. Now, if we were going to figure out how much EMF a generator could produce, we could do a kind of similar analysis to what we did with a motor. And we could start with our equation for emotional EMF that has to do with basically how big our loop is, how big our magnetic field is, and how much velocity there is. And if we work that in this situation, we could come around to this equation, which says our maximum voltage has to do with the area of our loop, the number of loops, the magnetic field, and this guy, which if you remember from our rotational motion chapter back in 151, this is our rotational velocity, okay? How fast our loop is turning. That tells us what our EMF max is. And again, with this situation, there are going to be parts of this cycle where there is not much, or where there's actually zero EMF. And then you're going to have a big EMF positive, zero, big EMF negative, zero, big EMF positive. Now you can solve that with brushes, as we did with a motor, or you can just accept that it's going to give you an alternating current. Okay, so if we use brushes, we can get DC current. More often, we use it to naturally, it produces this nice alternating current, which is what's coming out of your wall. And so it's very usable in that form. We don't need to worry too much about that equation there. Just I've worried more about the EMF max equation. But this tells you basically what the frequency of that alternation is going to be, which to have usable electricity, we want that frequency to be pretty dependable. Like 60 hertz.